Okay, good morning. Welcome to
FamilyMath number 618.
FamilyMath618. Today we're going to do some continue our project on continued fractions.
Alright.
Sorry for the rock banging noise in the background. So I'm going to show you one interesting property of continued fractions. Give me a normal fraction.
Like 1/2.
Yeah, but with slightly bigger numbers, maybe with two-digit numbers.
How about 13 over 19?
All right, I'm going to use 19 over 13.
Oh.
And I'm going to write this as a continued fraction. Okay? What would be the first term, do you think, of this continued fraction?
1.
1?
Because
Okay.
we're bigger than 1 here.
So it's 1 plus...
1 over something.
Well, 1 plus 6/13 at the moment.
1 plus 6 over 13. Okay, and now, so that's our first step. We split it into the integer part and then the part that's between 0 and 1.
Yep.
Then what do we do next?
Well,
we can
have
flip it.
Flip it.
Flip it. So what's this going to be when I,
So
instead
1
of 6...
plus 1 over 6 over 13.
Plus 1 over 6 over 13.
And then there's nothing to rationalize here.
It's already rational.
Okay.
But the 6/13 flips. And this goes away, so it's 13 over 6.
All right, so it's 1 over 13/6.
Alright.
Okay.
Yep. And then we have to do that again.
Okay.
So, I guess 13/6 has the 1 in it, so it's 1 plus 7. Actually, it would be 2 plus 7/6.
Or 2 plus 1, 6.
So 2 plus 1/6.
2 plus 1, 6. There you go. All right, and what am I going to do now?
Well,
Flip it.
I mean, you don't really need to do anything with this. You already...
Well, it's already a unit. It's already a unit fraction.
It's already a unit fraction. So 13 equals 1 plus 1 over 2 plus 1 over 6.
Nice.
And we can write this as a continued fraction. And what do you notice about this continued fraction that's different than the ones we did yesterday?
Well, it ends.
End.
It ends. So what do you think is going to happen when we start with a rational number and a continued fraction?
It's
Well,
probably going
it's-
to end, or maybe it'll repeat.
I think it's gonna. Well, yeah. Either. I mean, it's probably gonna end.
All right, why do you think it's going to end?
Well, a rational number can be. Any rational number can be expressed a over b.
Yeah.
So you can do something like this and make it, and then you can have it end.
Okay. Now the question of it repeating is an interesting one. Could it repeat? If we start with if we begin with a rational number, could we get it infinitely long? Could it repeat?
No, probably not.
No. Oh, okay. Why do you think not?
Well, I mean, the rational numbers, eventually, even if you have a really big fraction, I think you're going to just get it just down to a point where you have a 1 over something, and then you can just end there.
Yeah, we have to notice a few things along the way. So first of all, we start with 1 plus what was it?
6/13.
6/13. Okay, so I want to compare this number to this number, and there's a what's kind of one of the simplest observations you could make about those two numbers.
Well, this is smaller.
Okay, it's smaller. That's one. You see any other observations you can make about it?
They're equal.
What's equal?
I mean. Oh, you took just these two fractions?
Yeah, 19/13 and
They have
6/13.
the same denominator.
All right, they have the same denominator, and the numerator got smaller.
Yeah.
Okay, this becomes 1 over 1 plus 1 over 13/6. And now this turned into 2 plus 1/6, right?
Yeah.
So we want to compare 13/6 to 1/6 now.
Well,
Same denominator, but it just got smaller.
Okay, so same denominator, but the numerator again got smaller. So this can you put together the argument for why it will eventually end if we start with a rational number, the process?
Well, it seems to get smaller. The numerator seems to get smaller from each term to term, and the denominator stays the same.
Okay.
but that always has to be positive. It has to stay positive.
Right.
So eventually you're going to reach a point, the denominator is going to stay the same and the numerator is just going to go from a number to 1.
Eventually, we're going to get a 1 in the numerator. Right. You're right. But
And then we
there's
can
one extra thing happening. There's one more piece of what's going on that's kind of important to the argument. The numerators are always shrinking.
Yeah.
That's important.
Well, I guess the denominator.
So yeah.
The denominators get smaller from each. They get, I guess it went from 13 to 6 down.
Right.
From each
So
pair.
somehow the denominator is getting smaller along the way too. How is that happening?
Well, because once you reach a smaller numerator, then that numerator gets flipped to become the denominator.
Uh-huh.
And then the denominator, or the now numerator gets smaller again, and then that's flipped to become the denominator. And then
Okay.
it keeps just getting smaller and smaller.
Right. So you end up at every stage with a fraction that's getting, with the numbers, the numerator and the denominator are either staying the same, the denominator, the numerator is getting smaller, and then the numerator and denominator flip. Which means the original numerator and denominator are getting smaller along the way at every step. So the most this could take, the most number of steps this could take would be 19 plus 13, I guess minus 1.
Yeah.
But we'll say 19 plus 13, which is what, 32? So the most this could take would be 32 steps because it's getting smaller. Something's getting smaller at every step.
Yeah.
So there we go. So that's one observation, that with fractions, with normal rational numbers, the process stops. So this gives us another proof that the square root of 2 is irrational. Why?
Oh, the continued fraction doesn't stop.
Continued fraction doesn't stop. Okay, so I'm going to have each of you play with the Mathematica program and see what you discover about continued fractions, okay?
Alright.